Sí.
Bon dia a tothom. Gràcies per venir. És un plaer presentar a la Mar Flexas Esbert. La Mar és Senior Research Scientist a Caltech. La xerrada serà en anglès. Faig la presentació en català, però després ja canviarà a l'anglès. La Mar la conec de fa molts anys, que estava a la Universitat de les Palmes donant classes i va ser alumna meva. Jo em sembla que va ser estudiant de pràctiques al Departament d'Oceanografia Física i vaig tenir oportunitat en aquell moment de fer coses amb ella. Teníem una taula rotatòria allà i va ser força entretingut, i fer petits experiments de laboratori. I després, un cop va acabar, l'any 97, se'n va anar a Bangor a fer el màster en Oceanografia Física a la University College of North Wales, Bangor, i després va venir aquí a Barcelona i va fer el doctorat a la UPC sobre temàtiques, també amb estades allà a la Universitat Tècnica d'Eindhoven, a Holanda, sobre temàtiques de la inestabilitat del corrent del nord. Jo li deia, quin és el corrent del nord? El corrent català o balear. No sabia que es deia el corrent del nord, molt bé. Doncs després d'això se'n va anar, perdona, ja veig el Jordi Salat ja de seguida, diu, ostres, aquest Josep Lluís no sap res. Però bé, deu ser l'edat, Jordi. Parles del corrent del nord, penso que és la North Atlantic Current, però no té res a veure. Molt bé, després del doctorat se'n va anar a Imadea, on va estar fent un postdoctorat inicialment sobre el gir del Boran i va col·laborar molt amb diverses persones, entre altres l'Álvaro, fent-li moltes preguntes, interaccionant molt. I després va tirar endavant, ella va ser la persona juntament amb el Damià, però el Damià com signava, però la que ha fet totes les propostes en aquell moment, òbviament amb l'assessorament del Damià, totes les propostes i va fer totes les redaccions del conveni de col·laboració de la iniciativa espanyola dintre del que era l'any internacional polar. Llavors aquest va ser als anys 2008-2009, es va fer aquest any polar i va ser una iniciativa que va d'alguna manera reprendre tot el treball antàrtic en particular amb les campanyes CESACI que es van fer aquells anys que Espanya hi va participar mitjançant aquestes activitats que ella liderava juntament amb el Damià Gomis. També hi van participar altres investigadors com el Pablo Sangrado de la Universitat de les Palmes, però tot estava d'alguna manera arran d'aquesta iniciativa. Això d'alguna manera va ser l'altra activitat que es va fer després de les primeres campanyes que es van fer a començaments del segle, si mal no equivoco, amb el Marc Garcia i la gent de la UPC, que aquestes s'havien aturat perquè el Marc havia deixat la UPC i després es van reprendre, parlo sempre de campanyes d'oceanografia física, campanyes hidrogràfiques. I es van fer aquestes campanyes a començaments de la dècada del 2010, 2008, 2009, 2010, i després ja això des del 2013-2014 que ja no s'han tornat a fer campanyes d'oceanografia física antàrtica. Llavors, en part perquè la Mar va marxar i se'n va anar al JPL, el Jet Propulsion Laboratory de la NASA, i va estar allà l'any 2010 fins al 2015 o 2016 fent temes d'anàlisi de totes les dades que van sorgir d'aquest any internacional polar i juntant-ho amb aquestes observacions amb temes de satèl·lit i models numèrics. I des del 2016 està a Caltech, tal com us deia, com a Senior Research Scientist. Al llarg de tots aquests anys ha col·laborat amb moltíssima gent d'arreu del món, d'Amèrica també, d'Europa, és una persona de referència, ara és l'editor del GGR, però també ha seguit col·laborant amb molta gent de la casa, em consta, i aquí gent de molt diversos grups, o sigui que en aquest sentit és una persona de la casa. Doncs agrair-te, Marc, que estiguis aquí amb nosaltres i gràcies.
A vosaltres, moltes gràcies per convidar-me. Estic molt contenta d'estar aquí i de veure tanta gent coneguda de fa molts d'anys i de conèixer nova gent. I avui el que vos volia... clar, he de fer-ho en anglès. Today I'm going to talk about the Antarctic Coastal Current. This is the work that I've been doing the last, 20 years, but the interest in the coastal current is something relatively new in the Antarctic community because it's a very narrow and very shallow current that is very difficult to monitor in climate models, and its impact was not very clear until very recently. So it's relatively, it's a hot topic, you could call it. It's the work that we've been doing for the last 40 years. So what we are going to be interested today is in the role of the freshwater fluxes in modifying ice shelf basal melt rates. Or in other words, is how important is to monitor changes in sea surface height around the Antarctic coast. The circulation over the Antarctic margins is controlled by three main currents: the Antarctic circumpolar current, the Antarctic slope current, and the coastal current. The Antarctic circumpolar current shields the waters from the polar ocean, from subtropical waters. The Antarctic slope current follows the continental margin and separates waters offshore that are relatively warm from waters on the continental shelf that are fresher and colder. And the coastal current, as I said, is very narrow and very shallow, and is never or often not represented in circumpolar maps like this one. The interaction of these currents with the atmosphere and with the cryosphere, and with the cryosphere we mean sea ice and continental ice, is going to determine the dense water production rates. So in winter, you have a lot of heat loss due to the atmosphere cooling, so water becomes colder, and most importantly, you are forming sea ice. The sea ice, when it forms, it releases brine, so the waters in the continental shelf become very dense, because in cold environments, what determines the density is not the temperature, it's the salinity. So the amount of this dense water is going to be determined by the cryosphere, ocean, and atmosphere interactions. Once this dense water is produced, it starts spilling over the continental slope and fills the deep ocean basins. Once it fills or reaches the bottom, it's called Antarctic bottom water, and it's one of the main resources for the ocean to regenerate or to freshen the deep oceans in a process that is called ventilation, because you're bringing oxygen to the abyss. So you can imagine that if you are releasing fresh water over the continental shelf, or you are altering the freshwater inputs, you're going to be modifying also dense shelf water production, and this will have a direct impact on reducing Antarctic bottom water production. The Antarctic circumpolar current distributes this Antarctic bottom water around the global ocean. And therefore, the Antarctic bottom water is going to be playing a key role in the meridional overturning circulation. So once you have the Antarctic bottom water spreading around Antarctica, there is, this is the typical global thermohydrate circulation, so possibly you are bored of seeing this, but it's like you have the Antarctic bottom water upwelling towards lower latitudes, then intermediate waters approach again the south, and then they subduct again, this time as subsurface waters. And this complicated or three-dimensional process is key in in sustaining a healthy circulation. And then you can think that the reduced Antarctic bottom production because of the freshwater fluxes is going to change the meridional overturning circulation, because it's going to slow down all these conveyor belt mechanism, right? Another role of the Antarctic circumpolar current is that it shields Antarctica from these warm subtropical waters, so it protects the polar environment that is surrounding the Antarctic continent. But in the Atlantic sector of the ACC, there is a deep, relatively warm water called North Atlantic deep water that is able to approach the continent and to move onto the continental shelf straight away. For different reasons that I'm not going to discuss today, but this Antarctic circumpolar current, again, distributes this circumpolar deep water around Antarctica. And it is this warm water, when it goes onto the shelf and then approaches the coast and gets into the ice shelf cavities, that is going to be the main factor or the main responsible for melting the ice shelves, because most of the ice shelf is melting from beneath due to this warm water intruding into the continental shelf. What happens when you are melting from beneath is that you are starting to erode the base of the ice shelf. And by that, you are moving or retreating the grounding line. Once you are retreating the grounding line, you are destabilizing the ice shelf, and obviously you are going to start having a lot of accelerations, and you're going to start accelerating the ice sheet itself, the ice sheet flow that is called. And the ice is going to start accelerating towards the terminus of the ice sheet. And there, at the terminus, you're going to start having crevasses, and you're going to start calving, and you're going to start putting a ton of fresh water in different forms from the surface, because you have also surface heating. You're going to be melting from the surface, melting from beneath, accelerating the ice sheet flow, and all this process is the major contribution to global sea level rise. So understanding the processes that lead to this warm water approaching the continental shelf and going into the cavity and increasing basal melt rates is going to be key. The region where basal melt rates accelerate fastest is the West Antarctic ice sheet. This is a region that spans from the West Antarctic Peninsula, where Spain has the two Antarctic bases, down to the Ross Sea. In this map, we are showing rate of thickness change of the ice sheet, or the ice shelves in this case, right? And thinning is directly, made the connection that the thinning was mostly due to ocean basal melting, and is a direct signature of basal melt. So at the ways, the West Antarctic ice sheet, is where melting occurs fastest, and the region that is less studied is that is between the West Antarctic Peninsula and the Amundsen Sea, and that's for historical reasons. The United States has been, for many, many decades, studying the Amundsen Sea, and the West Antarctic Peninsula has been also very studied by most of the international community because of the Antarctic Treaty and the Antarctic bases that are around that area. The Bellingshausen Sea, not many people has been there, and for the first time, I'll say this later. So there are going to be two main points, or I think there are two main points relevant for understanding the observed increases in basal melt rates in the waves. One is going to be determine the pathways of intra and inter-basin exchange between the open ocean and the coast, and how this water moves downstream. That's the interbasin part. And then understand the role of freshwater fluxes in modifying basal melt rates across the waves. For the first part is what I was trying to say before, that the Bellingshausen Sea is a relatively unexplored region, but we have a ton of numerical models that suggest that this sea has a key role in setting water properties locally, and also on the Amundsen Sea and further downstream. However, the observations are not, we don't have plenty. So observation between the exchange between the coast and the shell break, and the intervention exchange still remains a bit sparse or unknown. So in 2019, we went for the first time, but it was the second cruise ever that was in the Bellingshausen Sea. In this case, we had a typical hydrographic cruise where we did CTDs, and we were sampling the main trough of the Bellingshausen Sea, which is called Belgica Trough. And on the left-hand side, I'm plotting heat content. Heat content is a measure of how much heat is available in the water column. In this case, due to the entrance of this warm water onto the continental shelf. There are two troughs. The right one is Lataidi, and the left one is Belgica. And most of this modified CDW is entering over the right-hand side, or the eastern side, of Belgica Trough. On the right-hand side panel, I'm plotting meltwater content. There is one way of calculating or estimating meltwater content using what is called an optimum multi-parameter analysis that was developed by Tom Chuck in the 80s. And you can estimate how much of this meltwater is in the water column. And in this case, it's not surprising that we found most of the meltwater next to Venable ice shelf, but because it's the only ice shelf we could sample, mostly because of sea ice conditions. And then we had a pool of meltwater exiting towards the continental shelf break over or along the western side of Belgica Trough, and then toward the shelf break, towards the Amundsen Sea. In 2020, we could go back, and in that case, we deployed an ocean sea glider. The sea glider is an autonomous underwater vehicle that it allows you to measure the same hydrographic properties, but with the fun part that you can navigate it from your computer. So you don't need to be on the boat, and you don't need to be next to the sea glider. So you can deploy it, and then you do the rest at home. And in the map, I'm showing the path of the sea glider in black. So we did some cross-slope sections and one large along shelf section. And in that cruise, we also took advantage of an amazing database that is an international community effort that is called Marine Mammals Exploring the Oceans Pole to Pole. It's a MEOP database. And there are a number of seals, in that case, with a CTD on the forehead. And they normally go to places that we could not go even if we wanted, because they go to foraging spots. So they go where there is food. And food is near sea ice, and food is near the ice shelves. So you have a ton of information in places that no boat can go. So one of the things we did was to look at this database and look at the regions where the seals were diving deeper than the bathymetry was telling us. And that's what I'm plotting in colors. And you can see that there are, close to the coast, there were many dives of seals diving even 500 meters deeper than what the bathymetry was telling you. And this is because one of the key observations in many ice shelves is that once you approach the continental shelf, you think it's flat. I say, yeah, I have my 500 meters here, is the shelf break, and I'm going to the coast, and everything is going to be flat. Well, no, you have submarine canyons that here we call troughs. But once you approach the ice sheet, so the sea ice front, the ice shelf front, the bathymetry is not flat. It starts deepening. And that deepening is going to be key for bringing this warm water down into the cavity and melting the ice shelf from beneath. So these colored deep blue dots indicate that most of the regions where we don't know the bathymetry are regions where there is a lot of food, obviously, because there is a lot of data, but also because there are these new troughs that we haven't seen before. In our case, what we were most interested was what I'm indicating here as seal trough. Before we analyzed this dataset, we thought that the Bellingshausen Sea was finishing at Belgica trough. But the seal data showed us that there was another trough west of Belgica towards the Amundsen Sea. And this trough had one very important thing. There was a direct pathway from the eastern tip of Abbott Ice Shelf towards the shelf break. So now we have what we thought was settled, like what we knew from the previous cruise and the importance of Belgica trough. And in this data set, we're going to see how important seal trough also turns out to be. In the next figure, I'm showing the hydrographic section along the shelf break. The top panel is potential temperature. The middle is the meltwater, and the bottom is backscatter. So you see that the meltwater is distributed in two different pools, or two separate pools, one on Belgica trough and one on the western side of seal trough. These pools are below the winter water, that in the top panel is represented as the dark purple color or dark magenta, because it has minus 1.7 degrees. And in the bottommost panel, in the backscatter, you can see that the two meltwater pools are correlated to different backscatter properties. And I'm not going to bore you with a lot of statistics, but these relations were shown to be statistically significant, and we could trust that they were really different pools of meltwater. Now, to determine where this meltwater was coming from, because we only had the data, remember, at the shelf break, we went back to the seal data. And in this case, we looked at, we chose randomly like 6 different pools of data in Belgica trough and in seal trough, and 2 more towards Abbott Ice Shelf. And we started with the Venable Ice Shelf data, the yellow pool. And we saw that in terms of water properties, in the TS diagram, you had 2 different families. One on the top right that had relatively cold Antarctic surface water, warm winter water, and not very modified CDW. And in the right panel, in panel B, we had warmer Antarctic surface water, colder winter water, and more modified CDW. These 2 groups of data in front of Venable Ice Shelf corresponded to different months. So this is data from 20 years altogether. We didn't look at interannual variability. But these 2 families were always separated by March and April, and December, January, and February. And then we started looking at the rest of the clusters and see where the data was matching these 2 families. And we found that it was pretty simple. The data from March and April was in Venable Ice Shelf, was similar from top to bottom to waters in front of Abbott Ice Shelf and waters in seal trough. Instead, data from December and January and February in Venable Ice Shelf was similar to properties found in the western side of Belgica trough. So this allowed us to separate again these 2 pools of meltwater and to separate 2 different coast to shelf pathways, or to propose 2 different coast to shelf break pathways. And in addition, we found that there was a lot of correspondence of all the water in Belgica trough, indicating a large recirculation. Then finally, to have a more complete vision of the Bellingshausen Sea, we calculated what is called dynamic height. That is a proxy for sea surface height. You basically integrate the density to one point of the water column, and then it gives you an idea of how high the sea surface is at this point. And when you do that, you find that there is an increment in the dynamic height towards the coast, indicating the presence of the coastal current all over or all along the coasts of the Bellingshausen Sea. But very interesting for us is that the coastal current, the gateway from the ice shelves towards the shelf break, was again along Seal Trough, not along Belgica Trough. And also, we found some hints that I indicated here with the purple arrows, or the pink arrows, that you had intensifications of sea surface height, or anomalies, towards Abbot Ice Shelf, indicating that there was a coastal current also towards the Amundsen Sea. So you would have two freshwater pathways towards the Amundsen Sea, one along the shelf break, along the Antarctic slope front, and one along the coastal current. And all this, obviously, because nobody went there before, is not that it was well known. So, the coastal pathway towards the Amundsen Sea, it was not very clear in the previous slide because it was like a bit broken. So, to understand if it was really a continuity or not, what we did was to take the seal data, and we did what is called the composite. You do put all the data you have, you collapse it in a bandwidth of a zonal bandwidth, and we did it in like 3 big chunks. And in the panels, I'm plotting salinity, and in white is the neutral density. And we could find the signature of the Antarctic slope front following the shelf break, and towards the coast, we could find the Antarctic coastal current as a signature of fresh water towards the coast. The middle panel, there is a lot of data that contradicts, so when you have this composite, the averaging blurs the presence of the coastal current, but when you break this section in orange, 96 West, into smaller sections, you can really see the continuity of the coastal current. So in this work, we identified both shelf break to coastal shelf break and coastal meltwater pathways from the Bellingshausen to the Amundsen Sea. We saw that differences in optical backscatter were associated to meltwater properties that were related to these two distinct coastal shelf break pathways, or could be related to different sources, so one from Abbot and one from Venable Ice Shelf. But obviously, with all this lack of information, we don't have a certainty of which is the truth, right? Or maybe it's both. Maybe you have both signatures there. And, but we saw that the main pathway to the shelf break was Seal Trough, and we could define like a new western boundary of the Bellingshausen Sea. So along these lines, we have a new proposal that is going to start next year to go back to the Bellingshausen Sea in 2027. And along these lines, I would like to identify possibly opportunities for European grants that I'm not very familiar how it works here because I've been too long in the US, but I would really like to focus on trying to find if we have opportunities to explore these questions from here. And maybe look more at multidisciplinary interests, so maybe how the impact of these freshwater fluxes contributes to biogeochemical cycles or carbon sequestration or carbon pump. The second part of what we were interested in understanding was look at the role of freshwater fluxes in modifying the basal melt rates. In this case, we are going to go back upstream at the West Antarctic Peninsula, which is a region that is very interesting because it has a lot of surface atmospheric warming and CDW intruding directly onto the shelf as well. These two things, or these two processes, produce a lot of fresh water input onto the surface of the ocean. And when we look at the forecast of coupled simulations, ocean atmosphere simulations, in the framework of the future increases of CO2, we find that we use SEMIP6 because it has a variable called runoff that we can play with and we can analyze. And what we did was to look at how much runoff is forecasted to increase in the next 100 years. So when we look at the time series from 1950 to 2090, or I think it goes to 2100, we find that in the historical record, in this tip of the Antarctic Peninsula, we have about 1 meter a year of fresh water. And that's a combination of everything: precipitation, surface melting, and basal melting. But in the current climate scenarios and the future climate scenarios, this freshwater runoff is going to increase up to 10 meters a year in 2100. So what we wanted to do were some, not realistic because it's a forecast, but some reasonable experiments to look at how much this freshwater input is going to affect the meltwater that is coming from beneath. So we took advantage of high resolution or relatively high resolution model called LLC 1080, which is an ocean state model that combines a ton of information from satellites and from hydroelectric cruises to do it's what is called an ocean state. So it's the best representation of the ocean that you can do in a global model. And we took this model and we took a small piece of it that covers from the Antarctic Peninsula to the gate of or to the gateway of the Ross Sea. So it covers Bellingshausen Sea and the Amundsen Sea. The peculiarity of this model is that it has 113 levels in the vertical. And this allows to to resolve very fine scale the Antarctic slope. Because if you are not able to reproduce or to refine the slope, then you cannot reproduce shelf slope exchanges. And in many models, there are problems along these lines because the resolution in the vertical is very expensive to run for the models, and they normally cut it down. So in this one, we could be able to add a lot of vertical layers, and we were able to add a parameterization of basal melt rates based on observations. So what we did was to look at this, or to deploy runoff at this yellow area and look what impact these anomalies of fresh water had on the way downstream. So what we found was in the top right panel, you have salinity at 100 meters in the run where there is no freshwater input. So the model without freshwater anomalies looks like that. That's the 27-year average mean. And the salinity shows a fresh signature next to the coast. That's what we interpret as the coastal current. And once you impose 10 meters a year, I'm just here using the difference between the 10 meters a year run and the no freshwater run, you have on the bottom left panel sea surface height, and on the bottom right panel sea surface salinity. So you can see that the impact of inputting fresh water at the tip of the peninsula is that you are raising the sea surface height near the coast all over the model domain, and you are decreasing the sea surface salinity by 0.5 PSUs. That is a lot because it's the highest freshwater run, right? So this doesn't happen today. It's going to happen maybe never, but hopefully. But it's to look at the extreme impact of these fluxes, right? So when you are putting extra fresh water, you are strengthening or you are enhancing the coastal current. Then what we wanted to see was the change in basal melt rates, right? So the top left panel shows you a time series for the 27 years of basal melt rates of all the ice shelves on the domain. In black is the no freshwater flux run, so the control run. The colors are indicating the different model setups, and the magenta is the 10 meters a year run. One interesting thing is that the interannual and the seasonal variability doesn't change. So you have the same seasonality and interannual changes, possibly because you can think, oh yeah, because atmospheric changes do not apply here. Well, we didn't know what we were going to have or to obtain, right? So to us, it was still interesting to see that everything was kind of coupled. And what you only see is that the basal melt just shifts higher and higher the more you put fresh water at the tip of the peninsula. If you do the average of these basal melt rates from year 2000 to 2019, you get the top right panel, where you have a dot, which is the mean, and then one standard deviation. And you see the freshwater input increases the basal melt rates across the ways in an almost linear way. The middle panels are sensitivity runs that we did to make sure that this was really the process beneath. And the most interesting run for me in these plots are the stop run, which is the one in red, in which we had freshwater input until year 2000, and then we hosed it off. So we stopped the freshwater. And you can see that once you stop the freshwater, it takes about 12 years for the basal melt rates to go back to the control run, which means that this what you expected as a positive feedback, because you have more fresh water creating or generating more fresh water, it's reversible. And that's very interesting from a climate point of view. In the bottom panel, you have the impact of each individual ice shelf to this freshwater forcing. And you can see that no matter where the ice shelves are, they are all going to be impacted up to 60% increase in basal melt rates from these West Antarctic Peninsula experiments, right? So when we looked at what was causing, or what was the physical process behind this, we saw that there was the fresh water that was leading to an increase of stratification right at the entrance of these ice shelves. So you took, what we did here was to take a section in the model right in front of each ice shelf and look at temperature and salinity, so stratification. And square is a proxy for stratification. So the more fresh water we were putting at the West Antarctic Peninsula, the more we were increasing stratification below the coastal current at very shallow depths, right? But this increase in stratification, what was causing was that was reducing the vertical heat flux. So you were pulling more warm water, because when you have a higher stratification, what you are doing is you are capping the capacity of exchange with the air and the ocean. So the more you increase the stratification, more difficult it's going to have to be for the warm water to escape vertically. And you were causing this warmth right only, and not in the total domain, but only under the coastal current. Together with the increased or the enhanced velocity, this gives you an increase in heat transport. So you are bringing more and warmer water into the ice shelf cavity, creating more basal melt, and therefore you are that's why you have more increase in basal melt rates, basically. This schematic just summarizes the experiment. So you have more glacial runoff in the West Antarctic Peninsula that is pulled over the coastal current. This coastal current brings all these seawater anomalies downstream. modifying the stratification and increasing the current strength and the amount of heat you are providing into the ice shelf cavity, and therefore melting more, right? So in these experiments, we concluded that non-local and local forcing can impact basal melt rates at individual ice shelves via these narrow coastal currents. And we think that the representation of these circulation features are going to be necessary for decadal scale prediction. Of course, it's very difficult to include these narrow currents into climate models because they are very coarse, but we think we need to highlight the need to understand these coupled systems. So it's not only atmosphere and ocean, or ocean and ice sheets, it's atmosphere, ocean, sea ice, and ice sheets. And we are sure that similar processes may be also relevant for the margins of Greenland. The ice sheets are different, but all this surface forcing and basal melt, I think, is going to be very interesting as well there. So the next thing we are going to do is to work on ISAT-2 as part of the ISAT-2 science team to try to monitor the variability of the coastal current around Antarctica. We have started, of course, in our favorite spot now, which is the Bellingshausen Sea, but we're going to extend it to the circumpolar region in the near future. And when I was preparing this talk, I just saw that a week ago, there was this paper published by Anne et al., in which they did kind of a similar experiment where they were dumping fresh water on top of in this case, the Antarctic circumpolar current. And remember we said that fresh water is going to impact the AMOC because it's going to reduce the Antarctic bottom water production. What they found is that dumping fresh water at the surface of the ACC was reducing the AMOC, but because this fresh water at the surface was moving north and impacting the North Atlantic regions, where you have the North Atlantic deep water formation, it was strongly reduced. And the region, or it was the largest impact of this AMOC reduction came from water from the Amundsen and the Bellingshausen Sea. So these areas, again, come as a key, and fresh water also comes as key in setting the AMOC properties and the thermohaline circulation. And although these ideas may seem new, they are not, because I also found this note on Journal of Marine Research. It's a page and a half, and it talks about the influence of freshwater discharges on the ACC, and they were already thinking that it would reduce the meridional overturning circulation. Back then, they couldn't prove it, but now that we have all these means available from high-resolution numerical models, in situ data, and satellite observations, it's a very nice moment to try to put them all together and understand better and forecast even better the present and forecast the future of the changing climate. And that's all for today. Thank you very much.
Thank you so much, Mark. So we have time for questions. From the floor, if you have any question. So just when people certainly will make up their questions. So when you were talking about these dynamic highs, during the different months, either summer or spring, these dynamic highs, in a way, it's a proxy for meltwater content, So you have higher dynamic highs when you have more fresh water. It simply raises and drives the continental.
Yeah.
The coastal current out.
Yes, that's what we think. But in that what we all think that happens is that in different times of the year, you would have one or other coast to shell break pathway. So you will have more or less meltwater, but it will have a priority for exiting through one trough or one canyon or the other trough. So this, it will be like a set in and set out of pathways. So you will have the bendable ice shelf is possibly melting more in the summer, which includes the two from the months of November to April, but it will have a different pathway if it melts more in the beginning or at the end of the sea ice melting season, because possibly you are, again, modifying the stratification of the system very close to the shell break, to the continental coast. So you have, by modifying the stratification, you can overcome more or less topographic features, and it has been seen in places like the Weddell Sea that you have different pathways depending on the sea ice setting. So that's something that we want to dig in more on, what are the different contributors to the freshwater cycle.
Yeah, and increased stratification in a way not only will inhibit heating from the atmosphere, but probably also increases the baroclinicity, yes. No? So it dives in more North Atlantic deep water, no? So that all can also be related. No?
And then you can also see that if you have an increase in the coastal current, you have more efficient way of carrying this glacial meltwater toward the shell break along the coast, and then you're going to modify or modulate more the ocean properties in the Amundsen Sea. So then you have to start thinking, okay, what happened in the Amundsen Sea? So it's going to be like a domino thing, no? So, and that's what we are trying to figure out. Why are these processes important, and can we figure out more things only with observations?
Thank you. Questions? Yeah, Pedro. Just a second, I'll bring this in. Thank you.
Thanks, Mar. Good stuff. The sea ice, I'd like to, you to say something about sea ice. Sea ice in Antarctica has been the counter argument for years, until 2019 pretty much, of what was going in the Arctic. In the Arctic for a long time has been decreasing, both in thickness and extent, but the counter argument was always, well, in Antarctica it's just going the other way. In 2019, it just changed completely the role. And what's from your point of view, and it's a significant source of fresh water as well, what's from your point of view the role of sea ice and snow over sea ice in the Antarctic?
You mean in terms of what is going to happen, or what is going to be the contributor?
Well, it's happening with the trend right now is just decline. Same thing as what's happening in the Arctic for a long time. The Antarctic was the opposite. It was increasing. Now since 2019, it's just going the other way, declining and disappearing. 2023 has been the minimum year in terms of the amount of sea ice in the Antarctic. In terms of fresh water, so you're talking about basal melt rates, and that's, the ice shelf is just dumping fresh water onto the ocean. But how much of that is modulated by the presence or not of sea ice and the amount of snow insulating material on top of the sea ice? Do you have any comment about that?
Well, I think...
You mentioned a little bit about brine rejection in the beginning, and that's all like the distribution of fresh water.
So the more you melt sea ice, obviously, you're going to increase the fresh water at the surface, and you're going to be reducing the capacity of the dense water formation, right? But in Antarctica, it's very different where the sea ice melts. So the impact of the sea ice melt is different if it happens close to the coast, next to the Polynias, or in the open ocean, that you're already in the ACC. Because the impact of how you're going to, so this fresh water is really dependent on your capability of bringing the fresh water down to the water column, right? So next to the coast, when you have the Polynias, it has been shown that an increased sea ice melt really caps and blocks the pollinia production. And this not only happens locally, but also downstream. So pollinias in one basin are going to be less powerful to produce dense shell water, but because of the coastal current, you're carrying this fresh water also downstream, and you're going to be modulating also pollinias downstream. In the ACC, the role, I think, is more towards how much you're going to suppress the upwelling that happens right at the outcrop of the density to the surface. So you're going to be modulating the Antarctic surface water. Below, you have the winter water. So you're going to be modifying all these air-sea exchanges, but it's through these different processes. So it's not so much a convection or a subduction, but also modifying an upwelling. So, and in sea ice, when it comes to sea ice, there are, around Antarctica, there are different areas that you produce more or less sea ice, but most of the sea ice in, for example, the Weddell Sea is transported by the wind. So you have a lot of sea ice in the West Antarctic Peninsula, but there is no production in the West Antarctic Peninsula. It's all in the Weddell. But because of the Weddell gyre, the torque of the gyre, there is a lot of advection. And then it's very interesting to look at where this sea ice that is coming from the Weddell, that they have pollinias there, brings all the sea ice towards the peninsula, and then how far into the ACC is the sea ice going to go. If there is not a lot of production, maybe it all melts in the South Scotia Ridge. But if there is a lot of production, it's going to be pushed farther out and into the ACC. And all these atmospheric factors, I think, they are very different if you are in the Ross Sea or in the Weddell Sea. So in one part is lots of advection, and in the others is not. It just stays there. So does that answer your question?
I think so. I was going to ask you, if I may, another one. Programmatically, NSF and NERC, UK and the US, they've had a huge, incredible investment into Thwaites, which you mentioned, or you showed in one of the places. That's finishing up, if not already finished. Is there any similar thing going forward?
At these levels, I'm not sure.
You were looking for European funding to continue this kind of work, and I wonder how much you can leverage one place with the other.
Yeah, I'm not sure. I know there are a lot of interest in the Weddell Sea again, but because of the inputs of bottom water, or it's deep water actually, that goes along the Antarctic slope front. So one key question is how the exchanges in between the different marginal seas is at the shell break. But in terms of, and because this slope front carries a lot of meltwater, right? But I'm not aware, I'm not sure how these things are going to expand. When I meant with the European grants, is like, because now I have, so when I started here, the Antarctic line, research line, I had the opportunity to meet a lot of the British and other countries' key persons on Antarctic research. And now that I was in the US, I had the opportunity to meet those in the US, and I'm more familiar with the processes asking for grants and all these things in the US than in Europe now. So if I will return, I will have to really start looking at what opportunities we have here, and I honestly have no idea if I will have to be only focused on Europe, or I can still, bring things together, or you have to do separate but parallel programs. So it's an idea, but it's not really anything concrete yet.
So should I continue in English, or can switch to Catalan? Well, if this is okay, so in Basque. Yeah. I'm curious about the really nice talk. I learned a lot from that area. I'm curious about the backscatter signal you see in your glider's transects. So is that an effect of simply the current, the shear stress of the current or suspending sediment, or it goes along with the type of water generated in this process of melting, and then could be the particles, the suspended particles that tracer for the pathways that the waters take while leaving these deep troughs under the sea ice out to the outer shelf or the mid-slope, and how the particles, how far they go. Is there any research on that direction, on the trace, on the pathways of the particles?
That's what I would love to know. So from the data we have, we didn't sample the backscatter layer. I mean, the glider only gives you the optical properties, but we didn't go and sample. So I don't know if you can, by sampling, determining the origin of the different pools and link it to different ice shelves, for example. So I think what we see could be both, right? Because it's an intermediate layer, and you could say, okay, the grounding line beneath Venable and beneath Abbott have different sediment properties, and that's what is giving me these two different pools. Or because we couldn't separate the water from Venable and the water from Abbott, so in this route that I drew between Venable, Abbott, and Seal Trough, I couldn't say it's Venable water, because in the TS properties, they look the same, Venable and Abbott. So you can say...
But you can add the suspended particles in the color properties of your TS, and then maybe you can differentiate the two pools.
Yes, but we didn't... I mean, the two groups fall into different depths and different density layers. But we didn't find, in the property diagrams, we couldn't find any evidence to say it's different sources or it's different pathways. And that's why I said it could be both, it could be only one, but we don't have any form to determine which is which. So, I mean, yeah, you can say the path through Seal Trough has different properties because it's shallower, so it's incorporating more sediment, and the current is stronger, so it's more capable of incorporating sediment. That's what we were kind of thinking, right? But in the end, in the paper, we didn't really, it was all speculation. So it was more of a, well, we have both, and we would love to know more, but we can't say for sure.
Thanks.
Some more questions? Yeah. Jordi, yeah. I was looking at him, I knew.
Thank you very much. It has been a lot of information that I cannot assimilate so fast. So I have just taken some pictures, general pictures, and I'm just to comment some general pictures. For example, the first one is that the melting ice is in the western side of the Atlantic, while in the eastern and central part is the reverse situation. Something like, if, I can imagine, that if you have a source of melting, like that you are just talking, in the Ross Sea and in the Bellinghausen Sea, and the Weddell Sea seems to export the possibility of reinforce the ice creation. So it's some different. There is any difference within the mixing of water from the Atlantic, from the Indian or from the Pacific, that can be, for example, the Pacific in that case, which is the part of belongs the Ross Sea, and may the water in the Pacific contribute to this situation of melting in that area instead of in the side of the Atlantic. That's one thing that I just was thinking, seeing to this. But probably there is no information about this. I don't know, because I am just out very, very far away from the Antarctic. I have never been there. I have read some papers, but some very few. The other thing that is the amount of fresh water. You are talking about 10 meters a year. That's an enormous amount of fresh water. Do you have any suspicion that in any place it can be such kind of fresh water flux? And a last comment from the comment from Pera. It's you have to ask for a grant to train seals to take samples of water. That's all.
That's a good point. So first you asked about the warm water, the influence of the warm water, right?
I don't know if it's warm water, it's melting conditions that may be not exactly warm water,
So
as you have, or even mixing of different water masses that converge in that point. Just this.
So meltwater studies are not very common still because it's very difficult to quantify the meltwater sources. So all that I can say is that yes, possibly the Ross Sea and the Weddell Sea have different meltwater patterns, but I think from numerical models we have a clear picture today that this meltwater that is locally produced is going to be exported along the different coastal and the slope currents around Antarctica. And yes, it's going to be difficult to see if this is the local meltwater that is influencing local basal melt, or is the exported meltwater that is going to influence local basal melt. So yeah, it's not, it's a to-do list. So.
What about the 10 meters of fresh
yes,
water?
so in that case, what we think is we are currently in 2 to 4 meters a year today. That's what the observations tell us. And to reach the 10 meters a year is going to be in the high end of the PCO2 scenarios. That's going to be like a maximum level. But our study, I think, shows that it doesn't matter if it's 10 or 6, you are still going to be increasing the basal melt rates in a proportional to whatever you are melting upstream. And the silver lining is that if we would stop this fresh water, we could maybe go back to historical levels, but it doesn't look like we're going to stop it, so not so much of a silver lining.
Mari, just curiosity, because I assume that all these dynamics should change significantly primary production. Is any, I don't know, in the glider you have any fluorometer or something as a proxy that could trace somehow the dynamics of that? No?
We don't currently. We don't have any.
But are you planning to include something?
It would be nice. That's, yes, that's, yeah, that would be really nice to look at.
That was quick, thank you.
Hi there, nice talk, and Claudia and the work here. So I was wondering, I don't think there is much basal information on there. So what is the baseline you can play with to be able to trace back this process in time and understand how fast this is going. So how strong is the distortion for any natural processes? That's my first question. And I also was wondering, I don't think is there any work looking at the paleoceanography on there to trace back, because in the past is this crucial water stratification has been observed in past.
Yeah, I'm not aware. Yeah, because I mean, I think, so this role of stratification in front of the ice shelves, that's really new. So that's something that is what we started showing, and it has not been shown before. So I don't have any idea on how it would go backwards in time, but it's a very good point. I mean...
Okay, thank you.
Thank you, Claudio. Well, I take the opportunity to just to mention that we have an ongoing project that Mari is collaborating. It's named SACO, South Atlantic Connections, and it's this next February. We're going to deploy 3 moorings at the end of the Weddell Sea in the Powell Basin. That's along the South Scotia Ridge, and we are collaborating with Mar closely, and also with people from the British Antarctic Survey and CICES and Senada. We're going to deploy 3 moorings there that are going to be a counterpart of the moorings, the 6 moorings deployed for a long time by the British Antarctic Survey in the Orkney Trench, east of the Orkney Plateau. So I also thank Mar for being part of this initiative, that also take the opportunity to thank the people from the Servicio Ingeniería Oceanográfica and all the people that is collaborating in this project. So, well, thanks again, Mari. It's been wonderful, and look forward to having you more time here in the future. Thanks
Thank you
again.
very much.
Bye.